All right, today we're going to look at section 9.6. We're going to talk about part 2, continuing with heat of reaction or enthalpy, and we're going to talk about how we can combine reactions together. Today we're going to talk about Hess's law, and in Hess's law it says that heat in a chemical reaction can be absorbed or released either in one step or in several steps. When there are two or more steps in the reaction, the overall enthalpy change, remember enthalpy is the same as delta, it means delta H, the heat of reaction. The overall enthalpy change is the sum of the enthalpy changes of all of the steps. So we're going to just add them together. There are really only two rules for Hess's law. The first is if you reverse the direction of a chemical equation, flip the reactants and products, then you reverse the sign of delta H. So if you flip the reaction, you flip the sign. And then the second rule is if a chemical reaction is multiplied by a factor, then the delta H is multiplied by the same factor as well. So in order to get your coefficients to be equal, maybe you need to multiply the reaction by 2, and so all the coefficients get multiplied by 2, then the delta H gets multiplied by 2 as well. So here's how we might use Hess's law. For example, here I want to know the delta H for this reaction. So I'm trying to find the delta H, the enthalpy change for this first reaction. I don't know the enthalpy change. I can't measure it directly for whatever reason, but I do have information about some other reactions that contain some of the reactants and products. So they may be similar, but they're not exactly the same. So I have equation 1 with its enthalpy change and equation 2 with its enthalpy change. So I'm going to combine equation 1 and 2 together in some way so that I can get the equation, my target equation. So I'm going to take the equations and I'm going to rearrange them if needed so I can get reactants on the left and products on the right. So in my target equation I had carbon on as a reactant, so I'm going to leave the first equation like it is. So the first equation, equation 1, I'm going to leave it in the same direction as I had it. Then for equation 2, I'm going to flip the equation because I want water as a reactant and hydrogen as a product. So I'm going to flip reactants and products. And so then I'm going to come in here and change the sign of my delta H. Now, the step 2, if an equation is multiplied to balance coefficients, then I multiply the delta H. Well, I don't need to do that because my coefficients are matching. So then that's all I need to do for that part. Then you're going to take your two equations then. Here we have equation 1. We left it the same way, and it's delta H. And then we took equation 2 and we reversed it, flipped reactants and products, and we flipped the sign. Then I'm going to do is I'm going to come in here and I'm going to just add the two reactions together, canceling out things that appeared on both sides of the equation. So I'm canceling out the O2s because there's the same amount of O2 on both sides. Then I'm going to add my reactions together, then I'll add my products together. Then all I do is come down here and add the delta H's together. And that's it. So here, let me do another example for you. Let's start looking at this. Here's the equation that we're after. So sulfuric acid yields sulfur trioxide and water. Notice the states of things. The two products are gases and the reactant is a liquid. It's important that the states match as well. And we'll see that here in a minute. So looking at equation number 1, I don't have any H2S or O2 in my equation, but I do have H2SO4, but the H2SO4 needs to be a reactant. So I'm going to flip that first equation. So you can see here I flipped the first reaction. So now the H2SO4 is a reactant, just like it is in my target equation. And you can see that I flipped the sign of the delta H. Looking at the second equation, I don't have either reactant in there, but I do have SO3 gas as a product. So I'm going to leave that equation just like it is. So you can see here I wrote the second equation in the exact same way it was written originally and left the delta H exactly the same. The third equation is a change in water, liquid water, to gaseous water. If you notice here in my target equation, water is a gas. In my second equation, water is a liquid, so that's not going to work. So I'm going to need the water as a gas in my third equation on the product side. So here you can see I have just written the third equation the same way as it was written earlier in the target equation. So liquid water as a reactant, gaseous water as a product. So the delta H. So now I'm ready to just add the two equations together. So when I'm adding them together, I'm looking for things that appear the same on both sides of the reactant, the yields arrow. So I can see H2S. Whoops, sorry. I can see the H2S is on both sides. I have two O2s on the reactant side and two O2s on the product side. And then I have H2O liquid on the reactant side and H2O liquid on the product side. So all of those appear on either side of the arrow, so we're going to cancel them out. So all I have left then is the target equation, H2SO4 becoming SO3 and H2O gas. So then I'm just going to take my delta H's and I'm going to add them together. So then I wind up with the enthalpy change for this equation to be 72.5 kilojoules. And if you recall our rules for adding and subtracting with significant figures, it goes by the least number of places past the decimal. So I'm going to round that up to 73 kilojoules. And that's how you use Hess's law. So I'm going to do another example. If you're feeling pretty comfortable right now, that's fine. But if you'd like to see the next example, that's fine too. All right, looking here, looking for the delta H for this target equation. N2 gas plus 2O2 gas yields 2NO2 gas. So I have three equations I can work with. So the first equation has my first reactant on the reactant side. So it's on the reactant side, so that's what I'm looking for. So I'm going to use my first equation just like it is. So now looking at my second equation. In my second equation, I'm looking for reactant or product. Here I have NO2. That's a product. I want it as a product anyway, so I'm going to leave my second equation just as it is as well. So now looking at my third equation. My third equation here, and notice it has a half O2, and that you'll see that sometimes when we're talking about enthalpy change or heat of reaction. It's okay, don't freak out about it. Then, so I'm looking for my O2. I want my O2 to be on the reactant side, here in this equation it's on the product side. So I'm going to need to flip the equation and then I'll flip the sign of the delta H. But I also need to multiply my equation by something in order to get my coefficient to match. So I have 1/2 O2 here. I want 2 O2s here. So what I'm going to do is I'm going to come in here and I'm going to multiply everything by 4, and I'm going to flip the equation. And then I'll flip the sign as well. All right, looking here now, I took the first product, multiplied it by 4, and made it a reactant. So I have 4 H2s. I took my second product, the O2, multiplied it by 4, and I got 2 O2s. Those are my reactants. Then I took the product, the H2O is now going to be my product, multiplied it by 4, and I have 4 H2Os. So I took my delta H, I flipped the sign, and because I multiplied it by 4, the reaction by 4, I had to multiply by my delta H by 4. So my delta H now is a positive 174.8 kilojoules. So now I'm just going to come in here and look at my 3 equations, add them together, cancel anything that appears are the same on both sides. So I have, looks like I have 2 NH3s on both sides. I have some 4 H2Os on both sides. And then I have a bunch of H2s. I've got 3 H2s here and 4 here, both on the reactant side. That makes a total of 7 H2s, which will cancel my 7 H2s on the product side. So then all I have left is my target equation, which is N2 plus 2O2 yielding 2NO2, and the delta H comes out to be a negative 82.7. Again, thinking about significant figures, looking at least number of places past the decimal. So I want to round that up to a negative 83 kilojoules. And that's Hess's law.